Hey, we're live.
Hello, I'm Justin Pivot and I will be your group presenter today. Alright, so this is our problem. What is the drift speed in a gold wire having an internal field of 1.5 millinewton per coulomb if the mean time between collisions is 2.5 picoseconds? Alrighty, well, that is great. So we have this fancy formula right here. It's on our sheet, but we just need this half. We got the fancy N. Okay, geez, oh well, it's gonna be a little crooked. And E. And this is tau. Yeah. And alright, there we go. So then, we're just gonna, we want to find the
Drift speed.
drift speed. Alright, so that's great. So we'll just, let's see, find that guy. So we'll get rid of that, and then divide by the area. So then we're left with alright, and that just happens to be all the information we're given. So their electrons, we're gonna assume, it doesn't necessarily say in here, but that's what would go through a wire usually. So RE is at 1.6 times 10 to the negative 19 coulombs. Our tau, so that's given to us in picoseconds, so we're going to convert that to, where did it go? There it is, okay. It's regular seconds. And then our electric field is in millinewtons, so. Alrighty, there we go, so then we just need to put it all together.
Oh, what's the mass of an electron?
Oh, there we go. Almost forgot that. And that is 9.11 times 10 to the negative 31 kilograms. Thank you. It's kind of like Dora. It's like, what's the mass of an electron? All right. So now we're just going to put all of these beautiful numbers together. Alrighty, so then you plug that in, we'll put it over here, and V is equal to, drum roll, there we go.
Oh, wrong drum roll. Cool. Okay, so that's the drift speed. A little bit about drift speed. Do you want to take the camera for a second? Cool. So, let's talk about drift speed for a second. There's too much stuff happening. So, let's see. We had a wire, right? And I'm going to do a blow up on the wire. So, here we got a wire. And current is the movement of electrons, right? So, let's draw our electron. And this electron is going to be moving. Well, okay, so let's back up. You have a gold wire, and all metals have a sea of electrons, right? They share their valence electrons, just because of what kind of element they are, or group of element, I guess. Chemistry, I don't know. Anyway, so you have a bunch of electrons, right? And because, I don't know why, these electrons are all going in different directions. Maybe at the same speed, I don't know. They do what they want. So they're going in all sorts of different directions, right? But as soon as you apply this electric field, whoops. So as soon as you apply this electric field, all of these electrons are going to start moving this way. So you're going to have a net movement this way. This is called, what is that? Oh, that's current. Okay, so you have a current flowing this way. And so, I mean, these electrons aren't going to stop like this one. If you want to zoom in real close. You have this electron, right? It's going straight up at time 0, right? It's not going to stop going this way and suddenly start going this way. It's actually going to get, if we want to go into vectors, right? You add this little vector, and then this electron has, you know, the net movement is going to be like this. Still going to be moving up, and as soon as it hits that, it's going to ricochet back down and all this other stuff. But this net movement right here, that's the drift velocity. Every single one of these is going to get that addition, you know, that vector addition. It's going to be like this. Any electron is going to have this, and they can go like this or like this or like that or whatever. It's arbitrary. It doesn't matter which one, where it's moving. But as soon as you apply this electric field, it's going to get this drift velocity, which is important for some reason. That's drift velocity, in case you were still confused.